Welcome, everyone, to our third installment in the AI learning series here at Ambiq. Today, we're going to talk about anomaly detection, which is a very important type of AI feature. I'll do a quick intro, and then I'll hand it over to Evan, who's the person who implemented the model for us. My name is Carlos Morales. I run AI at Ambiq. So briefly, what is anomaly detection? And purely from a definitional point of view, anomaly detection is the detection of outliers in data. So you take any kind of data series, you'll always have things that kind of fit the curve or fit the data, and then you'll have some outliers. And traditionally, initially, anomaly detection was used to get rid of outliers. Like you're a scientist or a statistician, you don't want the curve to be kind of fitting into all those weird points. But it turns out that outliers are very important. And so now we view them with value. And it is a hugely valuable thing to do in AI. It's you're actually being subjected to anomaly detection since you wake up until you go to bed. Credit card fraud, car engine lights, anything where you're looking at normal behavior and then suddenly something abnormal happens and you want to be alerted about that, tends to use anomaly detection. It is not a very, as these things go, it's not a very computationally intense task. It is a mathematical thing. You can use linear regressions, you can use other kind of simpler statistical methods or machine learning methods to implement anomaly detection. In our case, we used deep learning, which is kind of like using a shotgun to go after mosquitoes. Enormously satisfying, but sometimes not needed. But it's a great opportunity to show how you would use deep learning. And in our case, the kind of deep learning we used was an autoencoder. How to use that for a task like an anomaly detector. Another thing that came out of this exercise was that we were able to use something called semi-supervised learning, where you only label part of the data. And as Evan will mention during his presentation, in this case, we only labeled good data. For anomaly detection, that's very valuable because failures are few and far between, and you don't want to wait for an airline to fall out of the sky before you say, oh, hey, look, a data point for a failing jet engine. So what you do is you actually train on a partially labeled data as opposed to, say, a supervised learning where you have to label everything. There's another way of doing this, which is unsupervised learning, which is you let it go for a while and the model itself will learn what an outlier is. But in this case, since we had easy access to good labeled data, we did semi-supervised learning. And without further ado, I will turn it over to Evan. Evan, are you ready?
Hey everyone, I'm Evan. I have been an intern here at Ambiq over this past summer, and I have been working on creating an AI model to detect anomalies, but specifically, my AI model uses accelerometer data to classify different fan speeds as normal versus anomaly. So most fans, they have different speed settings with low, medium, high. So I considered the lowest speed of the fan as normal and everything else as an anomaly. So the steps that I took were to train a model to be able to make the proper classifications, and then to integrate the accelerometer with the Apollo 4 in order to test my model on live data. The dataset that I used was a public dataset from this GitHub. It contained 10 minutes worth of data collected for both normal samples and anomaly samples. And it had around 600 CSV files, each one consisting of 1 second's worth of data. And basically, each CSV file had a 200 by 3 array of floats containing the accelerometer data in the X, Y, and Z axis. And what I did with those values was I calculated the MAD, or the median absolute deviation, for each axis as input to the model. And the reason I chose to use the MAD rather than something like standard deviation or variance is because with standard deviation and variance, they're more susceptible to being affected by um, outliers and just non-normally distributed data, whereas MAD is a more robust way of measuring the spread of non-normally distributed data. So as you can see here in this graph, the blue dots, they represent the normal samples, whereas the red dots represent the anomaly samples, and they're very clearly separated. Moving on to the model structure, I used a very simple autoencoder neural network. An autoencoder is a type of neural network with two parts, the encoder portion and the decoder portion. So for example, if my model were working with images, the encoder portion would attempt to identify features important to the image, and the decoder portion would attempt to recreate the image. In my case, since I'm using MAD as the input, the output attempts to predict the MAD as accurately as possible, and then after I get the output, I compare it to the input um, by finding the mean squared error, or the MSE. So with the MSE, I look at the average MSE of normal samples and the average MSE of anomaly samples, and I create a threshold where anything greater than that threshold would be considered an anomaly, and anything less than that threshold would be considered normal. So my model itself is actually much simpler than this graphic here. Um, it contains one encoder layer and one decoder layer, as well as a dropout layer. A dropout layer is essentially a way to prevent overlearning or overfitting. So what it does, it sets the nodes in a layer to zero, the random nodes to zero, so that those nodes are not affected by the weight. And this is basically, it's like emulating the brain's ability to forget. Um, and one advantage of the autoencoder structure is that due to the nature of an autoencoder, I only train the model with normal samples rather than both normal and anomaly samples, because I want my output to be as close to the input as possible. So if I were to train it with anomaly data as well, it would make the model more inaccurate rather than more accurate. So um, the advantage to choosing an autoencoder style of um, a model is that we don't have to wait for the machine to break, which is pretty rare. After training my model, I had to deploy it onto the Apollo 4 EVB. In order to do that, I had to quantize my model first. Quantization refers to the process of transforming weights from 32-bit floats to 8-bit ints, which allows for more computational efficiency and less memory needed. Um, After quantizing my model, I converted the TF-lite file to a .h file with some Python code, and then I created a C file that stores the model in a tensor arena and invokes the model on a set of data. The set of data that I used was just the public data set from the GitHub, and then I flashed the code onto the EVP. After that, I found that my model, it was accurate. It was accurately predicting all the um, data correctly from my public data set. So the next step was to test it on live data. I used a sensor called MPU 6050 for that. It contained an accelerometer, and I collected data by incorporating an I2C communication link between the Apollo 4 and the MPU. I did so by just using code that the previous intern Rohan had written. He was using the same sensor, so it was pretty easy to incorporate his code into my code. And what I found was that after testing my model on the live data, I found that it was completely inaccurate. And the reason for that is because the fan that I used to collect data was completely different from the fan that the public data set had used. So this is actually something that all of our customers would have to deal with as well. They most likely wouldn't be using the model to detect different fan speeds. They would be using it to detect anomalies from some other machine. So they would have to collect data from that machine and train the model with that data. So that's what I did. I collected around 10 minutes worth of data, and then I started to retrain my model. So first, I partitioned my data set into 3 different data sets: the training data set, the validation data set, and the test data set. The training data set is what it sounds like. It's what I use to train the model with. The validation data set is it's a data set that I use as an unbiased evaluation to measure the model's fit. At the end of each epoch, I use it to fine-tune the hyperparameters of the model. And the test data set is the data set that I use last. It's what I use to measure the accuracy of the model after all the training has been completed. And after that, I plotted this graph. This graph is a graph of training and validation loss. And loss is essentially it's a way to measure the model's accuracy. So, for example, if my output was the exact same as the input, which is what I want it to be, the loss would be 0. So the lower the loss, the better. What you typically want is for the loss to decrease to a point of stability. Um, so that's what it's doing here. But one thing to know is that the training loss should usually be lower than the validation loss. I'm not too sure why mine is higher. It's something that I would want to look into more in the future. But some theories that I have are that it's just the way I train my model. If I were to increase the number of epochs, um, it may help lower the training loss. If another possible theory is that if I were to get rid of the dropout layer completely, it may also help make the model more accurate because right now I have such few inputs that the dropout layer might not be necessary at all. So I retrained the model, and this is where I'm at right now. It's not the most accurate, but let me give a live demo. So right now, I am calibrating the sensor. This is the fan that I have. It's pretty crude setup. I just take the sensor to the back of the fan, and it's connected to the Apollo 4. Right now, it's set at the highest speed, so it is an anomaly. Um, as you can see, it's predicting anomaly pretty accurately. It has some potential anomalies, but yeah, for the most part, anomaly. I'll turn it to the lowest speed now. And I get normal here. So what remains to be done is to improve the accuracy. Um, we don't want a model that's even just a little bit inaccurate. We want it to be as accurate as possible. So some ways that I could potentially improve the accuracy is to explore other model architectures outside of autoencoders. And another way is to explore different inputs, more specifically, inputs that are frequency sensitive.
Thanks, Evan. Um, uh, and thanks for attending our third AI learning series.